Welcome to 22nd lecture of video course on tribology. Today's topic is hybrid solution of previous approaches which we have used to solve a Reynolds equation. In previous lecture, we took two very simple cases by neglecting one term. One case neglecting term in x direction and in second case neglecting term in z direction. By neglecting those terms, we could get solution much faster and even a closed form solution. Those were the advantages of these two approaches, but sometimes we need to sacrifice solution accuracy, which is not permitted. That is why we are going to discuss one hybrid approach, which combines those two approaches which we have derived in previous lecture and gives a reliable result. So, in this lecture we will be giving first what are the concepts behind the hybrid approach and what is the validity of that hybrid approach. Just first slide, this lecture says that let us summarize what was approach 1 or when we were neglecting term in z direction. We say that we are assuming that x by z dimension in x direction divided by dimension in z direction. This ratio is equal to 0.1. That means, dimension in x directions are 10 times lesser compared to dimension in z direction. In that situation, partial differential equation which contain two terms, one term will be cancelled out and or neglected and other term will be retained, and based on this steady state Reynolds equation we can find out pressure profile, non-dimensional pressure profile in this term. Of course, this was for the some given data for the clearance, given data for the velocity and given data for the dimensions. For a very general case, we have to rederive it and so that we can utilize that derivation for any simple case which have a data. And what we obtain a pressure profile distribution, or say distribution of pressure profile, something like this. Say non-dimensional x coordinate, we took we say when we are plotting it, we divided in 11 divisions or 10 domain, 0 to 0.1, 0.1 to 0.2, and this is the non-dimensional pressure. We plotted these results. Similarly, we followed approach 2, where dimension in x direction were very large compared to dimension in z direction. I would say dimension in x direction is 10 times compared to dimension in z direction. So, this initially for the approach 1 this was a case, but now approach 2 this is our case. You can see this is 100 times compared to this approach, as means pressure distribution will change accordingly, and we found the pressure distribution for the given data something like this. By substituting h we can also represent in better manner, but three dimensional plot shows that this pressure distribution depends on x as well as the z coordinate dimensions, or we say non-dimensional z and non-dimensional x. H is a function of x bar. That is why we are getting x this direction, z this direction, and we are saying that as x increases, this pressure profile is increasing. That means, it is a convergent domain and more pressure will be generated. However, what are the drawbacks? In this case, we are not getting the pressure profile at the every point, because we have plotted only the varying by z value, and this is empty space. It is another thing which we can observe, that you take either approach pressure, non-dimensional pressure obtained by approach 1 or non-dimensional pressure obtained by approach 2. In either case, the pressure predicted by these equations will be greater than actual pressure. that can be seen by a simple algebraic relation like this. You say let us A and B, there are two terms and summation is equal to 100. Just for this example, we are saying that there are two terms, summation equal to 100. Why in this case there were two terms and we neglected one. The we neglected this second term in this equation. So, in other words, I neglect B, assuming the B value is low, it may be 0.1, maybe 0.5, maybe 1, but is a negligible compared to A. When we neglect this, then whatever the A value comes, that will be higher compared to what is given. We know these are the non-negative, they are positive quantities only. Even whatever the final value of the B, it will be having some finite value that need to be subtracted to get the value of A. But if I am neglecting it, I am directly getting value of A as 100. Naturally, by neglecting any term, whatever the term we get or whatever the value we get for A will be higher than the actual. This is the reason why we have written something like that. P non-dimensional pressure obtained for approach 1 or approach 2 will be greater than the P actual, non-dimensional pressure actual. So, we need to rectify it. That is why we think that we can hybridize T. We can find out the pressure profile by approach 1, we can find pressure profile by approach 2 and go for the harmonic combination of these two pressures. Now, what is the advantage? When we are using the inverse relation and we know if pressure is calculated by approach 1 or approach 2, the pressure will be more higher than the actual. So, keeping that in mind, we can find the pressure which is calculated by hybrid approach will always be lesser than P approach 1, P approach 2. That is obvious. We can take an example also. Say that let us say in the first case x by z is 0.1, that means dimension in x direction are 10 times lesser compared to dimension in z direction. Substituted it, we neglected this and we evaluated the pressure profile by equating this term 1 first term equal to right hand side term. We find some pressure profile, assume this is a pressure approach 1. Now, if just for sake for getting the some data, I neglect the second term and try to solve this term, what will happen? This 0.01 when it will come this side it will be 100. So, if I calculate by neglecting first term pressure profile, I will find pressure profile approach by pressure approach 2 is equal to 100 times compared to non-dimensional pressure obtained by approach 1. Now, we can substitute in a hybrid approach, you say P approach 1 as it is and we can keep this as a 100 P approach and represent pressure profile, non-dimensional pressure profile in terms of pressure obtained by approach 1. It will turn out to be 99.1% of pressure obtained by approach 1, which is the lesser than approach 1. So, that is giving some validity, this result may give good results. Similar case for the when the dimension in x direction are large. So, dimension in x direction is 10 times large compared to the dimension in z direction. In that situation, we neglect this and this is equal to 0, will turn out to be this side. Whatever the pressure profile comes, we represent as a pressure, non-dimensional pressure by obtained by approach 2. While coming to the pressure obtained by approach 1, we can get that will be 100 times this, because here at least it was divided when we were neglecting this term. While we neglect this term, this 100 figure is also going away. Naturally, the pressure profile obtained by equating this term with this term will be 100 times compared or will provide the pressure 100 times. So, again the same thing. Now, in the we can substitute the value in this hybrid approach expression and what we obtained pressure profile in terms of pressure obtained by approach 2. This again same thing comes, is a non-dimensional pressure obtained by hybridization will be 99.1% of pressure obtained by approach 2. And we know in this case approach 1 is reasonably correct, and in this case the approach 2 is reasonably correct. However, the situation may arise for the intermediate stages, assuming the x is slightly higher value, and this ratio is 0.25. When this ratio is 0.25, quite possible a pressure obtained by approach 1 will not be very good or will not give very good reliable results. Similarly, in this case, if I assume the x is 4 times compared to z, then again this approach alone will not give the good results, but hybrid approach generally gives a good approach because it is combining the characteristics of the two approaches and trying to give better results by minimizing the drawbacks of these approaches. Now, as in previous slide I mentioned that those expressions were for the typical one example. To apply hybrid approach, we need to derive pressure distribution or pressure non-dimensional pressure without the dimension initially, assuming that we do not know dimensions, and once we have pressure profile we can substitute the dimension and get the overall result. So, to do that, let us start with approach 2 first. We say find the pressure distribution or pressure expression for approach 2, or you say using approach 2. This is the expression here x, earlier we were using the 100 value, while here we are using x square by z square. These are the non-dimensional terms, and we can rearrange. We can take the z square this side and divide it by x square, rearranging a term. So, now there is a clearance dimension or maximum dimension in z direction, max dimension in x direction, and additional point is that h bar film thickness does not depend on value of the z or z coordinates. That is for a steady state one directional motion only. Otherwise, it may depend on the z coordinate. For our case, for present assumptions, we can take it out without really differentiating with respect to z bar, because h is not a function of z. So, we rearrange this term. Here the h bar comes, and which is the only function of x. Now, we can integrate it as this whole term does not depend on the z, and this also does not depend on the z. As it does not depend on the z, we can treat this as for time being as a one constant, and when integrate it, it will be z bar plus one integration constant, because we are not using substitution or we are not using any closed dimension on this. That is the first integration. Now, subsequent to that there will be second integration. Now, you can see that we are not substituted any value of any dimension, and we are getting only an integration constant term. So, there is a one integration constant, there is another integration constant. To get the pressure expression, we require value of C1 and value of C2, which are integration constants. And of course, for the overall pressure distribution, we require geometry, we require taper angle or all other necessary dimension which are listed over here, which are expressed in this expression. So, finding the first constant, we know very well at the end condition generally the pressure profile or pressure will be 0, that will be the ambient pressure. So, we can say 0 pressure at the start value of the z, that the z is equal to 0, z 0, z 0, that gives clear cut expression for the C2, C2 will be 0 in this case. Coming to the second point, we say again when z bar is equal to 1, or we say that z is equal to the maximum value of the dimension, that is a capital Z, then pressure will be 0. We can write the z bar equal to 1, z bar equal to 1 here, rearrange, and we find the constant C1, integration constant, that is a negative term, and that is depending on the film thickness variation with x, and clearance, dimension in z direction, dimension in x direction, and film thickness itself. When we substitute this in Reynolds equation, or we say that derived non-dimensional equation, non-dimensional pressure expression P bar, we can substitute Z1, we substitute Z, we can substitute C1, and we can substitute C2. What we get something like this, we can name it that this has been obtained by approach 2. There is a clearance, single clearance only, well the Z effect of the dimension is a square form, effect of the dimension in x direction is in a cubic form, film thickness is also cubic, and here we are finding z square minus z bar, and this satisfies both what we say initially, pressure should be 0 when z bar is 0. Substitute 0 here, substitute 0 here, overall pressure will be 0. Then we say when z bar is equal to 1, we say 1 here, 1 square minus 1, that is again will be 0. That means satisfying this satisfies both the boundary condition which we substitute and got this expression. So, this is expression. Now, we can substitute the value for some example. We are continuing the same example which we have done for the approach 1 independently, approach 2 independently. Of course, so this will allow us to find out whether we have made any mistake in derivation or not. So, here again same data, we say the leading and trailing film thicknesses are 40 micron and 20 micron respectively. Sliding speed is 20 meters second, viscosity 10 millipascal second, find the pressure, and as these data are given to us, we can find out what will be the non-dimensional film thickness that we did earlier also. This is the 2 by 3 in bracket 2 minus x bar. X bar will vary from 0 to 1, that means even the final value with the x bar is equal to 1, film thickness is not 0, it has a finite value and that is a 20 micron. When we differentiate, because we require differentiation of h with respect to x for this expression, we differentiate it, we find this is only negative minus 1 will be the differentiation of this. So, overall it will turn out to be minus 2 by 3. Now, we can substitute value of h bar, value of first gradient of h with respect to x, and we can find this expression, right. So, clearance value has been also used here. We have assumed the clearance is the average value of 0.02 plus 0.04 divided by 2, that comes out to 0.03. Z square we are not substituting because this example yet does not give the dimension values about x direction or z direction. So, z square, while h is given, that is in the terms of 2 by 3, 2 minus x bar. So, cube of that will be 2, cube of 2 will be 8, cube of 3 will be 27, and 2 minus x bar is in brackets. So, cube will be like this, x cube we are keeping as it is. Substituting the value of this gradient, that turn out to be 2 minus 2 by 3, and this term will be as it is. After simplifications of this equation, what we get is something like a 0.27 divided by 8 in terms of z bar, sorry, in terms of the z and x. Of course, z bar and x bar are also there, but we know very well this will be varying to find out pressure distribution, while this will remain constant. We cannot vary this for pressure distribution. Now, let us take a case 1. We say in this case thrust bed dimension is 100 into 10, 100 mm in x direction and 10 mm in z direction. So, 10 mm in z direction, 100 mm in x direction, that is giving figure something like 0.27 divided by 80,000, and this is for the pressure distribution expression. We will retain it as it is. Take case 2. Here the dimension are just reverse, dimension in x direction is a 10, while dimension in a z direction is a 100. So, pressure expression will slightly change. Here say instead of here 0.27 we are getting 2.7 and instead of 80,000 we are getting only 8. So, pressure obtained by this approach will be much larger, or in other words we should choose dimension in such a manner which pressure gives a lot of value or maximum value in that. This gives an indication we want a higher pressure, we should go ahead with this approach, this kind of dimensions. Now, that was for approach 2. Similar kind of expression is required from approach 1. So, we say the pressure expression using approach 1. In this case, this is a simple relation, but here h bar depends on x bar. It is a function of x bar. We can integrate it, and when we integrate it, we initially we do not have expression for h. So, we are keeping as it is in the same form, integration plus some constant, integration constant. On second time integration, this h bar q will be coming in the denominator. We need to integrate whole expression, numerator come denominator, plus another additional constant, that is C2 constant, integration constant in this case is C2. So, we have two integration constants, we need to figure out value of C1 and C2 to find the pressure expression. To help that, to find these values, we have pressure boundary condition. Pressure boundary condition is a 0 value and the P bar is equal to 0 at x bar equal to 0. That means, the initial at the entrance pressure is 0. Similarly, pressure at the exit will also be 0. So, we have pressure variation at 0 value of the pressure as a 0 at x bar equal to 0 and pressure equal to 0 at x bar equal to 1. To find out this pressure distribution, we require film thickness expression, and that can come with some example only. It will, and this is a generalized one. Now, based on a given problem, we can find out value of h, we can find out a gradient of h and substitute this, integrate and get the results. To do that, again we can take same example, and using that example you can say that we can find pressure distribution using approach 1. Same example here, the leading and trailing film thickness 40 micron, 20 micron, sliding speed, viscosity of oil, and based on this expression we know film thickness expression will be non-dimensional film thickness 2 by 3, 2 minus x bar, and gradient will be 2 minus 2 by 3. Now, we have these values, we can substitute, and we can substitute h also. In addition to these values, we have these pressure boundary conditions. So, let us start. First thing, we substitute value of gradient of h with respect to x, that is a minus 2 by 3, which is coming here 2 minus 2 by 3, and this is c by x we are maintaining as it is. As this is constant, we can integrate easily, that as there is no pressure and there is no x bar term coming in this whole expression. So, it will be simple integration to x bar. So, first term in this case, this whole term after integration will turn out to be minus 2 by 3, capital C is a clearance, x capital X x bar plus this integration constant, and we substitute this value also 2 by 3 in bracket 2 minus x bar cube form. Now, there are a lot of common terms in this expression, we can rearrange, and we after rearranging, like when we take 2 by 3 common, naturally this will be multiplied with this constant, so 3 by 2, and we can change the symbol. So, instead of integration constant 1, we will say the integration constant C3, because it will be multiplied with additional term which are constant. So, constant into constant makes a constant. So, instead of saying only the constant C1, we will say C3 constant, but we will use only one term. That is right. After rearranging this, taking common, we instead of writing C1, we are writing now C3, which is being multiplied by 3 by 2, and we took a common term. In addition, there is in a denominator 2 minus x bar, which is integrable, and we need to convert numerator into the simple form. What we did, the c by x bar is already one term, we added a term 2 over here and subtracted the same term. We are adding one term, we are subtracting the same term. So, that overall is 0, but it will make much more meaningful integration to us. So, after arranging this integration constant is C3 and plus another constant C2. We need to determine C2 value and C3, but this simplification is required, so that it helps us to get a easy integration, and that simplification gives c by x, one term is 1 divided by 2 minus x bar whole square. Second term is C3 here, and this is minus 2 capital C by x, that is also arranged, and rearrangement gives this as a integration term. This is a non-integratable term, is just a simply constant will be moved out. Similarly, like this, now this one integration of this, another integration of this term, and after integrating we know this will be simply 1 by 2 minus x bar, minus term will be here, and then this after integrating minus x, it will be again minus 1. So, minus 1 will turn out to be plus 1, same thing over here. This term after integration will turn out to be 2 minus x bar whole square, and minus 2 into minus 1. So, minus 2 into minus 1 will turn out to be 2. So, this is the one, this is a term. Now, we have this expression in terms of two constants C3 and C2. Now, simply we can find out what will be the, if I say x bar equal to 0, what will be the pressure distribution? We know that will be pressure distribution of pressure, non-dimensional pressure will be 0. Similarly, we can substitute another condition when x bar is equal to 1, then again the pressure will be 0. Substituting this, what when rearranging, we say pressure is 0 here, and here the 2 minus 0, 1 by 2. Similarly, in this case also 2 divided by 2 minus 0. So, it will be 2 by 4, 1 half, 1 half and 1 half of this will be common, that is why it will turn out to be 9 by 8, right. And here it will be c by x, here C3 minus 2 into c by x. So, 1 this is minus 2 c by x, there will be 1 c by x over here, so 1 will be cancelled out and overall turn out will be C3 minus c by x. This is not going to change, it will remain constant. So, C2. So, first expression which contains C2 and C3 both are here. Same thing for x equal to 1, p is equal to p bar is equal to 0. This is when we say 2 minus 1, it will turn out to be 1, 1 by 1 is equal to 1. So, simply will be in this whole term will be equal to c by x. Coming to second, this is a constant term divided by multiply by 2 divided by 2 minus 1, that will be 1. So, here it will be 2. So, 2 c 3 minus 4 c by x, and there is a one term here c by x. So, overall term will turn out to be 2 into c 3 minus 3 into c by x. Now, we have two terms c 2 and c 3, and we have two equations. We can simultaneously solve these equations to find out integration constants c 2 and c 3. This is shown out here, when we can directly say the c 2 can be represented in terms of c 3. We can say c 2 is equal to minus 9 by 8 c 3 minus c by x, and when we substitute this value of c 2 over here, what we are getting, c 3 is equal to 5 c divided by 3 x. Now, once I know the c 3, I can substitute value of c 3 in this expression to find out what will be the value of c 2, and that c 2 is turning out to be a negative value, 3 by 4 capital C, the clearance, divided by capital X, dimension in x direction. Substitute and we get approach something like this, or we say pressure expression something like this, 3 by x 3 by 4 capital C divided by capital X, first term, second term and third term. We can verify that whatever we have obtained earlier with the data, this is giving the same value, this expression is going to give the same value. Now, we can assume can start with the case 1 and case 2. First case where the dimension in x direction is much larger compared to the case 2 or compared to the dimension in z direction. Substitute these values, what we get is the expression something like this. And in second case we are assuming the dimension in x direction are 1/10 compared to dimension in z direction. Naturally, so in this case expression will change. Here the x is 10 times more compared to this, and that is coming in a denominator. So, this is 0.0009, while here it is a 0.009. This clearly says that in this case dimension in x direction is not as high as dimension in this direction. Or in the case whenever the sliding velocity is in x direction, we should choose a lesser dimension in x direction to get a much more higher pressure distribution. Now, we can apply these expressions for our hybrid approach, and we already evaluated pressure if we using the approach 1 and pressure using approach 2. We can combine this, and what we get a expression slightly complex compared to approach 1 and approach 2, but this is going to provide the better results compared to approach 1 and approach 2. So, we substitute here, and now we can see the pressure is coming we are getting in terms of x bar as well as the z bar. The both the dimensions are playing a role in this pressure expression. Similarly, for the case 2, here we are also getting same thing. You can see the pressure distribution in this case, this is higher compared to this one. Similarly, this is higher compared to this one. So, pressure distribution will be on the higher side using this dimension, this kind of dimensions, or wherever the sliding velocity is there, dimensions are lesser, we will get the better result compared to tangential direction, where the pressure there is a no tangential velocity in that direction. So, it should give the better results by choosing this. It can give some information how to optimize this kind of type of pairs. Now, if we try to evaluate the results by hybrid approach and compare with approach 1 and approach 2, the results are now to be this is what we say expressions for the results obtained by approach 2, this is the results obtained by approach 1, and these are the results obtained by the hybrid approach. You can see the slight variation only in this. Can clearly see here this is in a decimal form 0.6, while here it is not in decimal form, but this is 10⁻⁻⁷, this is 10⁻⁻⁶, right. So, only slight variation, otherwise it will be 10 time variation. Coming to the this side, again a slight variation compared to this, but we are saying that pressure distribution obtained by hybrid approach is pressure profile is lesser than the obtained individually by approach 2 for a case where the approach 2 has been recommended, and similarly pressure distribution obtained by hybrid approach is lesser than the pressure distribution obtained by the case where the approach 1 is recommended. So, this is approach 1 pressure profile obtained by approach 1, and we say aspect 10 in the very high value, aspect 10 is a low value and it should be recommended here, but even after that we are finding that there is a lot of variation in this approach. So, hybrid approach is a reasonably good gives a reasonably good results compared to approach 1 and compared to approach 2. However, we cannot just believe on that, but we can get the more and more results, and we need to verify this against some established approach which does not take any assumption or say lesser assumption. It is like a finite difference method, which we say it is going to take more time, but it can provide the reliable results. So, we need to understand what will be the comparison in that case situation also. Now, this is what we have mentioned earlier, the approaches comparison of approaches. This is what previous slide was it was shown on this data basis. Here the dimension are changed. So, instead of 100 mm in z direction, we take a dimension 25 mm in z direction. So, only that is going to change. There is a change in dimension only in z direction, there is no change in other direction. When changing in z direction, if we find the pressure approach, pressure obtained by the approach 1 does not contain any z dimension. So, it should not change the overall value, and while pressure obtained by approach 2 should change the value, and that is because it contains z as well as x, while approach 1 is containing only the capital X. So, if there is any change in x direction, then only the pressure will change. Otherwise, changing the dimension in z direction is not going to change anything, whether the dimension is 10 mm, 15 mm, 100 mm, 1000 mm, pressure expression remains same. It is not going to change, which is a problem with approach 1. Now, when we compare this, you can see here non-dimensional pressure obtained by approach 1 is higher value, is coming roughly around 28 into 10 s to 2.8 into 10 s to minus 4, while hybrid approach gives almost this value is around 1.8 and 10 s to minus 4. So, 2.8 versus 1.8, and if we go through the number of books, they suggest that this approach is going to give very reliable results, but it does not happen really. Hybrid approach gives much better results compared to this approach. I agree that this approach 1 is a simpler compared to approach or hybrid approach, but hybrid approach provides a reliable results. Of course, again and again I am emphasizing hybrid approach is going to provide as a reliable results, but we need to prove it, and that is why we say that we will be taking help of the finite difference method where assumptions are lesser. Our only assumption is that we need to choose a more number of nodes, and assumption is that as the space decreases, the accuracy will increase, or nodal space is higher, then accuracy will be lower. While hybrid approach, we get a quick solution, and we do not discretize or we do not divide in number of domains, obviously a number of nodes. So, hybrid approach has an advantage from that point of view, and finite difference from accuracy point of view, we can establish hybrid approach, we can compare hybrid approach pressure expression with finite difference method, that is going to give us some confidence. Of course, in this slide we are showing that even when the x is equal to 40% of the z dimension, hybrid approaches give them a much lower value compared to the non-dimensional pressure obtained by approach 1, which is drawback of the approach 1, even though this ratio is not very low value, sorry, in this case it is not very high value, still this approach is not giving the good results, right. However, just to other extreme cases, we can see z. If I say that instead of pressure obtained by the approach 1, I want to see what will happen when I obtain the pressure distribution by approach 2. You can see here the pressure maximum value is coming roughly around 0.042, is almost 100 times compared to, or maybe say 200 times. Here the pressure profile is at 2.8 10 s to minus 4, while here it is a 0.042 10 s to minus no, there is no 10 s to minus 2. Yeah, obviously the 4.2 into 10 s to minus 2. So, the pressure distribution in this case is much larger compared to more than 100 times compared to what we obtained from this. So, this is should be neglected whenever this kind of dimensions are there. Of course, if I put an order, this is the lowest worst case. this comes in the middle order. If we do not have much time and we do not have computer facilities, or we do not have do not want to go to hybrid approach because it is not a very stabilized approach or stable approach. So, in that case we can go ahead with this, but understanding the merits of the hybrid approach, we can recommend, yeah, this approach is good approach and it gives a reliable results. Only thing is that it should be able to give us a results comparable to the numerical result compared to the finite difference method or finite element method, whichever method we use, it should be able to provide the good results to us. Right. So, when we have that kind of thinking that this hybrid approach should provide us the reliable results, then we can say let us start with the finite difference method. It is a two dimensional. In our earlier lecture, we considered only the one dimensional case and try to get the solution based on one dimension, which are the dimension in one directions are only sufficient to be considered, not in two direction. However, in this case to get a more accurate result, more reliable result, so that we can compare with the hybrid approach, we require dimension in the both directions. So, this is the first term, second term and third term, all are in non-dimensional form. We already understood how to discretize, how to present the pressure profile at the nodes, and here the I and j are the nodes. So, h here h bar was is calculated the some I node plus half, the half of the node, which is the hypothetical, but we can find out the geometry at the hypothetical node. This is the p I plus 1 node ahead of the desired node, and here h bar I minus 0.5, that is a one node, is a half node behind the node desired node. Similarly, over here p I minus 1, that the one node behind we say that which has already passed compared to the existing node or desired node. This is the desired node, and this is the spacing in x direction. The del x bar is spacing in x direction. Coming to the second term here, now one easier one thing is that if this h bar does not depend on the z, then I do not have to do this kind of discretization in terms of h. I can simply move out h cube. We say h I j cube can be simply moved out of this differentiation, and then we need to discretize only this term. But we are not taking the assumption here. For derivation, we are counting both the cases, or where the h also depends on the z. So, what we can write here is again a similar form. Instead of I, here we are writing j. Okay. So, I will be as it is, and j will get additional node, the j plus 0.5, the half node for the j direction. Similarly, here instead of p I plus 1 j, here we are writing p comma j plus 1. Same thing over here, and again same thing over here. Next, similarly, we can take a central difference method for this pressure and this film thickness gradient h I plus 1, h I minus 1. Now, many times what happened? Many times h as a given as a film thickness, and this expression can be directly figured out. In that situation, we do not have to really differentiate, we do not have to use a finite difference method. Assume that we know already h as 2 by 3 and bracket 2 minus x bar. We can simply differentiate, we do not have any complexity in that differentiation. So, I can directly use those values. I do not have to really convert, or we say do not have to discretize and represent this gradient in terms of nodes. We can directly write in terms of I j, but not in this way. We can simply substitute that. Now, what is what was taught earlier, that when we substitute all these pressure expressions, we should get the pressure P I j, which is a desirable pressure at any instant. The P I j is a pressure to be determined with help of pressure at the 4 neighbor nodes, and these are the constant, these are geometry dependent constants, while this is the source term. So, we need to figure out what is the A I j from this expression, we need to figure out what is the B I j from these expressions. Cij, Dij from these all expressions which we have written, and finally comes a Eij, which can come from this expression. And of course, if you see that here even the Pij here and Pij here, there are two terms Pij, that means we have to take common of this Pij, and there will be some term with a multiplication factor, and we are not writing any multiplication factor over here. That means, whatever the factor comes over here, that should be in denominator on this side, or we need to rearrange this expression in such a manner whole geometric constants turn out to be in terms of A, which involves the terms which are also on the left hand side. To explain this, we can use some expression. However, to solve this equation, there will be a number of unknown to us, but we require few knowns to also to us. So, we know the boundary conditions, so pressure will be known to us. Without boundary condition, we will not be able to solve it, but in addition, this will be an iterative scheme. And initially, we all assume that pressure at the all the nodes equal to 0, unless we know what is the pressure profile, or we are able to estimate by some other method. If we are able to estimate by other method, we can give that an initial value. However, we are not able to estimate, then the simplest one is that you assume that all the pressures are equal to 0 at the start, and through iterations only it will develop, it will come to some solutions. But we need to provide some boundary condition, what will the pressure at the exit, pressure at the entrance, which are generally known to us, or what many times we are known what will be the supply pressure, at which pressure this pressure liquid is supplied to the interface. Those things are known to us, right. So, when we try to incorporate those values using to find out the A, B, C, D in terms of geometry, we need to substitute all the expression what we got in previous slide, expression for this first term, expression for second term, expression for third term. Now, substitute all this, assuming that H is not depending on the Z, that is simplifying over the case. Here we are saying the H bar cube Hij, and bracket is without any H. So, it is a Pij plus 1, Pij minus 1 minus 2 Pij, the simple one, and in first case only the all H terms are appearing. Now, we can rearrange this term by we can rearrange in terms of Pij. We substitute value of Pij on one side and get the results accordingly. And this is what we say, that you take a common of Pij the both the side, and this has been done here. Pij, we have one term 1 and 2 term over here, that is come this side, yeah, this one and this one. And similarly, this is also a term which will be multiplied with the Pij, that is a term which is coming over here, and this is on a negative side. So, we have taken to the right hand side, and this term will be on the left hand side. So, we are just rearranging now. We know very well this is a Pij, and the right hand side or in the left hand side, not a single term contain a Pij, while on the right hand side only the term contain the Pij pressure profile, and all other are geometric constants, which will not vary with iterations. It will not vary with iteration. However, all the pressure terms will vary with iteration, but all other terms will remain constant. So, once we know this expression, we can equate. We can say we divide whole this term or to this expression, and we should get a pressure expression in terms of Pij. We will continue it this kind of approach in our next lecture, and try to complete the finite difference method and compare with hybrid approach, and try to establish whether hybrid approach is going to give reliable results to us or not. Thank you. Thanks for your attention.